All right, so in this video, we're going to talk about percent ionization, and then we're going to talk about weak base equilibrium. So this is a follow-up to our weak acid equilibrium lecture, so you'll need to watch that one first in order for this one to make sense. Okay, so when we talk about percentages, you know that percentages are part over the total multiplied by 100%. So in the case of weak acid ionization, we're going to take the H plus concentration at equilibrium, and we're going to divide it by the initial concentration of that weak acid and multiply it by 100%. So this is basically a weak acid equilibrium problem first. So we need to go ahead and solve for that. So here we have acetic acid. Just to keep it simple, I'm going to write the short generic formula, HB, and we write out our equation first. And the initial concentration is told to us to be 0.2 molar. Okay, this goes here. Okay, there's nothing here at the beginning, and the value that we get, we don't know it yet, so we call it x. So this is plus x plus x. This is minus x on that side, so 0.2 minus x. Okay, we write our expression next. Ka is equal to the concentration of H plus times B minus over the concentration of HB. Now remember, an equilibrium expression requires equilibrium concentrations. So if we substitute in what we have so far, we get 1.8 times 10 to the minus fifth is equal to x times x over 0.2 minus x. All right, and this is where we stand. Now, remember from our simplification rule, when the order of magnitude, this is 10 to the negative fifth, and this is 2 times 10 to the minus 1, when there's 4 orders of magnitude or 3 orders of magnitude different from these two, and there are, then this can go away, and that simplifies the math. Instead of having to use the quadratic, we don't need it anymore. So we simplify because this guy here simplifies, and that means 1.8 times 10 to the minus fifth is equal to x squared over 0.2, and that makes this a lot easier to solve. So multiply both sides by 0.2, so 1.8 times 10 to the negative fifth times 0.2. This would be 3.6 times 10 to the minus sixth is equal to x squared. If we take the square root, x, which is equal to the H plus concentration, is 0.001897. We're going to call it 0.00190 molar. All right, this is H plus. So to find the concentration, we need to take this concentration and divide it by our initial concentration to give us our percent ionization. So percent ionization would be 0.0019 over 0.2 times 100%, right? And this is what we're doing right now. So divide by 0.2 times 100. So our percent ionization is 0.95%. So basically 1% ionization for that problem. If the concentration was 0.2 at the beginning, our percent ionization is about just under 1%. If we did this problem again, but we had a different initial concentration of 0.001, we can solve for percent ionization again, and we can see how that changes. So we'll do this one in a different color. Let's just use purple. Okay, so same setup, HB, H plus, B minus. So this would be 0.001 here. That's 0. That's 0. This would be x. This would be x. This would be 0.001 minus x. The Ka would be 1.8 times 10 to the negative fifth is equal to x squared over 0.001 minus x. Okay, to solve for x here, in this case, we have 1.8 times 10 to the negative fifth, and we have a 1 times 10 to the minus third. Minus third, minus fifth are only 2 orders of magnitude apart, so we cannot use the simplification rule. We must use the solver. And we'll go over how to use the solver, and that'll be a different video, but I'm just going to use it now for the sake of expediency. Okay, so x squared divided by 0.001 minus x, and then 1.8 times 10 to the negative fifth, 0. All right. In this case, the value of x is equal to 1.25 times 10 to the minus fourth. Now remember, we set x to be equal to the concentration of H plus at equilibrium. So our percent ionization is going to be this number over our initial number, our initial concentration, times 100%. So in this case, we will get 12.5% ionization, which is a lot different than 0.95%. And the reason is that the lower the initial concentration gets, the more the acid separates, because there's more room between particles so they don't recombine. So when there's more room to spread out because they're less concentrated, the percentage of dissociation will be higher. And that's the takeaway from that. All right, so that's percent ionization. Now let's just apply equilibrium in the context of bases. And a lot of what we're going to be doing here looks exactly the same, just different at the end. So for bases, if you have a base and you don't know what the formula of the base is, the base will react with water to produce hydroxide. And the reason why it reacts with water to produce hydroxide is that the negative charge that attracts an H plus off of water, and that's how the OH minus is formed. So your products are HB and OH minus. The rules for base equilibrium are the exact same as acid equilibrium. We write an expression where we write your products over reactants. And again, you cannot use the liquid because it has no measurable concentration. So this is known as the base dissociation constant. And hence it's written as Kb, because B is for base. So if Kb increases, the more base dissociation increases, and thus that's a sign of a stronger weak base. Okay, and again, the end product, when you're solving for x, x is going to be equal to OH. So let's do 2 problems here for this base equilibrium. Okay, methylamine. Here we have a 0.1 molar solution. They gave us the pH. They want to know the Kb. All right, so start with an equation. I could use the actual methylamine equation since they gave it to us. So CH3NH2 plus water. Because this is a base, it's going to end up taking CH3NH3 plus OH minus. It took an H plus off of water, and that's why the number of H's went up, and that's why the charge went up. In the water, the charge went down because it lost an H positive. Okay, so this is our equation. The initial concentration is 0.1. We don't write anything underneath water because water has no measurable concentration, so just put an X through that. Okay, so plus X, we don't know how much it's going to change by, so we just use X as a placeholder. 0.100 minus X. All right. The goal is to find, oh, I'm sorry. I just realized we do know the value of OH minus. Let's modify this table. We actually do know it because the pH is given, which means we can find POH, which means we can find OH minus. So I overlooked that, but we can fix that now. So 14 minus 11.8 is going to be POH of 2.20, and OH minus concentration is 10 to the negative POH. So 10 raised to the negative 2.2. OH minus is equal to 0.00631. And that's then going to go down here. That is the value at equilibrium for both of these because it's a 1-to-1 ratio between them. So this will increase by 0.00631. This will increase by 0.00631. And on the reactant side, 1-to-1 ratio, that will decrease by the same amount. So 0.1 minus that, 0.0937. Okay, we now have all of our equilibrium values. So now we can solve for the Kb value. The Kb expression is the products of over the reactants and we have all those values, so let's plug them in. 0.00631 times itself is squared over 0.0937. And our Kb is equal to 4.25 times 10 to the minus 4. Okay, let's review what we did. We had a base, we wrote an equation, the pH was known. Because the pH was known, the pOH was known, and thus the OH minus was known, and we can put that in at equilibrium. If we know we went from 0 to that amount, that is the amount of change, and that's how much this will change also, which is going to end up being the same number. On this side, this is how much it's going to change, and that's why the number at equilibrium is lower. And then write your expression, products over reactants, substitute in your values, and solve for Kb. Okay. And last one. The Kb for ammonia. So here the Kb is known. They want to know these values. Okay. So ammonia is NH3. When NH3 reacts with water, it takes an H+, it becomes NH4 with a positive charge. OH minus is the other product. That's what's left of water. Set up table underneath. We start with a 0.2 molar solution. Nothing goes underneath the water. Okay, now because we know the Kb, we don't know the value of change, so this is where we do plus x minus x. All right, our expression, NH4 positive times OH minus over NH3, and we don't use water, so we now substitute in the variables that we have. So 1.8 times 10 to the minus 5th is equal to x squared over 0.2, and I'm just like before, this right here, the 0.2 and the 1.8 10 to the negative 5th, this is 4 powers of 10 different, which is far enough where I don't need to include this guy here. I can just ignore it. And so that makes this easier to solve. So this will be 3.6 times 10 to the negative 6th is equal to x squared, which means x, which, because this is a base, is equal to the hydroxide concentration at equilibrium. X is equal to 0.001, we'll call it 19. All right, so now we have our OH minus concentration, which means our pOH would be easy to find. We just take the negative log of that, and that's 2.72, which means our pH is going to be 14 minus that, which would be 11.28. And that is how we do base equilibrium. The rules for equilibrium are the same, whether it's an acid or a base. The thing you have to pay attention to is the outcome, what x is equal to. If it's a base, x is equal to OH minus, but if it was an acid, x would be equal to H plus.